mention.
All right, thanks for having me. It's an honor to be here at KITP. Let me say a few words about the premise of this talk. So the question that's always in the back of my mind is organizing topological order in 2+1D by computational power or complexity. And that, for me, sometimes means quantum, sometimes means classical, as we'll see today. And I'm somebody that comes from condensed matter motivations, but I'm going to talk about this in a way I hope if you're interested in topological order holographically, or if you're interested in sort of more broadly what generalized symmetries can do for quantum computation, that there will be something to take away from this talk today. And the kinds of tools that I use to study this problem are very mathematical. So I'm interested in what can I say about anyons in bosonic topological order today using modular tensor or modular fusion category theory, some topology, and we'll see a little bit of classical complexity theory. So my talk is going to fall into two parts. I want to share some things I've been up to lately. And the first part of the talk will be me telling you about the complexity of a very specific theory, really a family of theories. And then in the second part of the talk, I'm going to tell you a relative result. So I'm going to tell you about a tool that I think is useful for placing different topological orders on the same kind of quantum computational hierarchy. And I think as I was writing this talk and listening to everyone else speak this week and at the program, one of the themes that's emerged for me has been the relationship between invertibility or non-invertibility and complexity in various senses. So I think that's a sort of a unifying theme here. So I should say a bit more about what kinds of problems I'm going to be tracking, because there are lots of different computational problems encoded in a topological order, or a TQFT. So, of course, these theories, the natural computational paradigm is quantum. So what we're all more used to thinking about is what kinds of qubits can I build with my anyons and what kinds of logic gates can I get on them. But there are other problems that you might study. And today, I'm going to be focusing on invariance of links, knots and links, and invariance of closed tree manifolds. So if you have access to your modular tensor category, these are additional problems you can study that we'll see sometimes may be more accessible and can tell you something in case you don't have a good grip on the kinds of gates you can build. And of course, any kind of computational problem you're studying, you can consider it exactly or approximately. I'm only going to be talking about exact computation today. And it's worth mentioning there are several people in this audience that share similar motivations. Sort of this work is I feel complementary to, but from a different point of view. So asking questions like, okay, given a trivial product state, what kinds of topological states can I prepare with, say, finite depth quantum circuits? So that's sort of another, I think, approach to a very similarly motivated question. And whenever there's any overlap, we should all kind of be saying the same thing. All right. So this first part, as I said, I'm going to tell you about the algorithmic complexity of a very specific family of TQFT invariants. And I'm going to be talking about Terai, Vero, Westbury state sum TQFTs. So what I have access to is a fusion category. And so I'll circle back at the end and say, maybe comment briefly on what this says about the topological order, namely the Drinfeld center of that fusion category. So as you may know, there are lots of sophisticated ways to think about these fully extended field theories in 2+1D, but that's not the point of view I need to take. Need to be very down to earth if you're going to say something about algorithmic complexity. And so I just want to think about this in terms of the underlying data structures to the input to this problem. So, data for a skeletal data for a unitary fusion category and a simplicial triangulation of a three-manifold. And so, if it's unitary, maybe I need to tell you a little about quantum dimensions, but I'm really thinking about a fusion category in the way that I tell it to a computer, right? And similarly with my three-manifold, which is fancy T, I'm thinking about it as a collection of tetrahedra glued together, or even more sort of basically, right, a collection of vertices, edges, faces, and tetrahedra. And so just to remind you, I'm sure people have sort of seen this before, and this is in very broad strokes here, but you have a state, you have a labeling of the one skeleton of your triangulation with elements of your label set, your simple objects. And for every simplex in your triangulation, you make an assignment of some fusion category data. And you sort of allow this assignment to range over your whole triangulation, and then you sum it up. That's the state sum. So for a state here, for the moment, I'm sort of allowing myself to label my triangulation arbitrarily. But of course, if the fusion rules aren't enforced sort of at faces, those terms are 0 and they drop out. But the reason why I want to write it like this for the moment as an arbitrary sum is that it becomes clear that this formula is exponential time in the worst case scenario, or in full generality, right? It's exponential in the number of edges, which, if you prefer to think about the size of your three-manifold as the number of tetrahedra, you can relate it and show that it's exponential in that as well. So, okay, this classically gives you an exponential time algorithm, but then it's interesting, at least it's interesting to us, myself and my collaborators, to ask about the landscape of these TQFT invariants as you vary the input fusion category. What can you say? So let me tell you a little bit about what's known. I can't promise this is a complete list of references, but some of this will be familiar. And so I want to start down at the bottom of this diagram with when my fusion category is Vec A an abelian group, invertible symmetries, if you will. Those can be computed in polynomial time. Those are easy. That makes sense to us because if we think about the anyons that gives rise to, those are abelian anyons. I can't do much with them without playing some tricks with non-trivial topology. So invertible symmetries, easy TQFT invariants here. Now, if you want to introduce non-invertibility, there are different directions you could go in. You could ask about making the group non-abelian, and there's actually some room for more results in this direction. But it's a result due to Cooper-Berg and Samperton that at least when G is non-abelian and simple, these are NP hard to compute. And I should back up a second because I know none of us probably are, trained complexity theorists, myself included. So even this picture here, this bit of a polynomial hierarchy of classical complexity classes shown on the right is a little bit of an oversimplification. For us, if I say something's NP, it means it's an easy problem, efficiently computable in classical time. And if I say something's NP hard, it means it's hard. So, great. So introducing non-invertibility in that sense, things can get hard. You might ask about, non-abelian things that are not simple, and there's a few results in that direction. But arguably, an easier direction to pursue if you're just trying to introduce a little bit of non-invertibility is to talk about Tambari-Yamagami fusion categories, right? I'm just going to take Vec A, I'm going to throw in one more non-invertible object. We usually call it M, right? Has that Tambari-Yamagami fusion rule. And it's a result from almost 20 years ago of Kirby and Melvin that these are hard to compute, these when the underlying group is Z2. So just take the very simplest example and you get something hard, even though you've just thrown in one non-invertible object. And in work in progress with Samperton and Clément Maria, we expect to be able to show that this is true for A more generally, okay? You're just making this problem harder in some sense. You don't expect it to get easier. So at least from this point of view, you introduce just a little bit of non-invertibility and your invariants become hard, okay? But we were able to say something quite nice about this hardness and how it's controlled. And so there's a lot going on this slide. Let me try to break down what I think is the salient part. So we basically come up with what's called a fixed parameter tractable algorithm. Mason, you got a question?
I just had a question about the complexity classes.
Yeah.
This may be more resolution than you wanted to discuss, but I thought NP means that you should be able to check the answer easily.
Yes.
And I'm kind of surprised that you would be able to check the results of these state sums easily.
Yeah, so The actual complexity classes that are considered here are sort of counting problem versions or function problem versions of these complexity classes. So the actual complexity class is called sharp P, and so it's really more of a counting problem, which you might think of as, okay, I'm counting these state sums. So it's not exactly this complexity class, but yeah, because we don't expect P to be equal to NP, problems that are at least as hard as NP complete problems, like we don't expect to be able to find polynomial time algorithms for, and so that's our notion here of.
So is it more correct to replace the words, like the NP with sharp P?
Yes.
Okay.
Yes.
Thanks.
And if that makes sense to you, just do that for the rest of the next 2 minutes or whatever. Yeah. Thanks for your question. Okay. So we were able to say something nice. We came up with what's called a fixed parameter tractable algorithm, following some ideas of Maria and Spreer in some previous work. And basically what we can do is we can control the exponentiality of this algorithm. So you see this O2 to the beta 1 n cubed. So that n cubed part is polynomial. There's this 2 to the beta 1. So we can take what's hard, we can take the failure for this problem to be computable in polynomial time, and we can package it up in this beta 1, which is the first Betti number of the 3-manifold with Z2 coefficients. So for us, let's just think about it as some measure of how big our 3-manifold is. It's some topological invariant of the 3-manifold. It turns out itself can be computed in polynomial time. So it's a pretty nice parameter. And in particular, what this algorithm tells us is that if we have a bound on the Betti number, how big our manifold is, actually this is a good algorithm. And so if you're interested in computing, Tambari-Yamagami state sum invariance, maybe not a good use of your time to go and look for a quantum algorithm to do it, because there's a classical algorithm that's actually not bad in practice. So before I move on, I maybe want to point out one thing about this result that I think is interesting to me. The idea sort of boils down to taking our state sum, which now I want to think about as a sum over admissible states. So I'm really enforcing those fusion rules on my 3-manifold triangulation. And I want to partition it up. I want to collect all the states that map onto the same cohomology class, the same first cohomology class. What happens is, because of that Tambari-Yamagami fusion rule, if you think I have an M, I hit it with an abelian object, I get M back, right? I take M, I fuse it with itself, I get the sum over things in my abelian group. So if you ever look at a trivalent vertex, you always have 2 M's lying around or 0 M's lying around. And so if you think about your one skeleton of your triangulation, those M's are always going to be dual to a cycle on your manifold, just because of that sort of Z2 graded structure of Tambari-Yamagami. So this would have maybe been a little clearer with the picture. But the point is, we partition the state sum into a state sum at a cocycle. And then we show that we can actually partition it into a state sum at a cohomology class in a uniform way. And then we show that once we've chunked it up in that way, what's left over, the partial state sum at a cohomology class, can be computed in polynomial time. It ends up being something called a quadratic Gauss sum. Natty, yeah.
Does this assume that there's no other algorithm which is faster? So some bright person can come and say, look, there's a totally different way of computing it. Yeah, absolutely yes or absolutely no?
Great question. So this is an algorithm. We don't have a negative result that says this is the best possible algorithm. But the fact that we, A, expect these invariants to be hard, and B, have controlled it in this topological parameter in such a nice way, sort of suggests that this may be the nicest thing you could hope to say. And if somebody comes along and they have a better algorithm, we don't expect it to be able to get rid of this exponentiality. We expect it to be sort of polynomially equivalent. But yeah, someone absolutely could come up with a better classical algorithm.
Okay, and is that a statement that works for any manifold? Or can I imagine that for a subset of the manifold, there could be a more efficient algorithm? But maybe not for the generic manifold.
Yeah, I mean, I'm always thinking about a closed-oriented 3-manifold. We haven't thought about that. Yeah. Oh, you mean for a specific family of three manifolds where,
So in physics, it's very common that there's a problem which is very hard to solve, but on the subspace of the parameters, it is solvable.
Well, and in fact, I think one interpretation of our result says that if you know what the Bettian, if you know what three manifold you want to compute this on ahead of time, well, in polynomial time, go and compute its first Betty number, then you actually have a polynomial time algorithm. Mm-hmm. So if you sort of have a fixed specific manifold in mind, or a class of manifolds in mind that are bounded in this sense, like this is a sense in which this is a good algorithm. Yeah, thank you for your question. So we reduce this to something that's computable in polynomial time. It's called a quadratic Gauss sum, which is going to feel very familiar to all of us because this is something that's computed from the data of a finite abelian group in a quadratic form, and you must be thinking, that sounds like an abelian theory. And you're right, but it's not on A and Q that you might be thinking of sitting in that trivial component of my Tambara-Yamagami fusion category. It's actually a pretty gross subgroup of a big direct product of copies of A, and it's something carved out by, Q is something carved out by the Tambara-Yamagami bicharacter. Nevertheless, the reason I am bringing this up is because sometimes, we see formulas that look like a gauging of a partition function, and they involve some kind of summing over homology or cohomology classes, and this kind of has a feel to it like that. But it's more of a feeling, and so it's just an observation. But I don't know that there's necessarily anything concrete to say about gauging in this case, but it sort of has a resemblance, this idea of, or de-gauging, partitioning a state sum. Okay, so I want to move on and switch gears, and I want to tell you about something totally different, which I've come around to thinking of as a tool for classifying topological order by complexity in a couple different senses. So let me tell you about it, and there are people here that have heard me talk about this before, but if you haven't, I want to explain. It's called zesting. Mathematically, it's a way to take a braided fusion category and cook up another one. But let me tell you the main idea, because the main idea is not too hard to get on board with. In order to make this machine go, I need my, I'm only going to be thinking about modular fusion categories. I need it to have an A grading, which I want us to think about as a trivial asymmetry. And I also need to have some abelian anyons lying in the trivial component of that grading. And if I have both those things, there's something you can try to do. You can take your original fusion rule, and this notation is going to look a little weird. It's going to look more like defects, and I'll mention that in a moment. Take an enyon X in the A graded component and enyon Y in the B graded component, and I'm going to write down a new fusion rule over set lambda, where I fuse with lambda AB, so that's a subscript E. So I change the fusion rule with some abelian enyon in the trivially graded component. And if I want to do this consistently, this needs to be a 2 cycle. And I'm keeping the labels of the anyons fixed. I'm not changing that. The rank is preserved here, but I am changing the fusion rules, and in general, you will change the duality structure. So what zesting is really just a theory, an abstraction and parametrization theory that says, okay, if I try to change the fusion rules in this way, then when can I and how can I categorify to the right level of structure that I need for this to describe an enyon theory? And so you see a bunch of data there, lambda nu TF. I'm not going to worry about that because this idea, I think, can be appreciated if you think about treating these anyons as defects with a trivial symmetry, and then just making sure you consistently change the symmetry fractionalization class. And so you should think we're really changing something about the invertible structure sitting inside this enyon model. And I think that's what I want to say about it for now, just the main idea. I'm just changing the fusion rules by a 2 cycle valued in abelian anyons, but you probably want to see some examples or hear me mention some examples if you haven't seen this before. And so the very smallest example that I can tell you about is that all 8 unitary modular categorifications of Ising fusion rules are related by this construction. Great. So a simple example, something we already kind of take for granted, like, yeah, all these things are basically the same, but they're related in this way, among other ways. But zesting can also do more interesting things. So you can take modular tensor categories that come from, representation theory of quantum groups. So I can take some Chern-Simons-like thing, I can zest it, and I can get something that is not of that form anymore. It does not come from that kind of family, that kind of theory. And so it can, we saw in the previous example, it can change the Witt class, but it also can move you outside of nice families of topological orders that we usually sort of think of together. My favorite example is that it can produce what I call modular isotopes. So it turns out that mutual and self statistics, so the S&T matrices, the modular data of anyons they're not a perfect invariant. So there are counterexamples to this being a perfect invariant. And the first ones we know about don't happen until like rank 49. So they're really big, but they come in a nice family. And it turns out that we could show that zesting produces these examples. So that these are quite subtle examples, but again, they're not terribly different, right? They have the same mutual and self statistics. So it's going to be kind of hard to tell these apart. And here's a way in which I can construct them. Yeah, Natty.
No.
So I believe the answer is no. Yeah, you can. Oh, sorry, thank you. So the question is it that we just aren't able to rule out that it comes from a Chern-Simons theory, or whether we can prove that it doesn't? And I think, so in restricting the scope of this question just to like modular tensor categories, the things that we know come from, from this quantum group representation theory, I believe it's at the level of a proof. I mean, we sort of have a good handle on all the possible things that you can get of that form, and you can show that it is not of that form. So I think the answer is yes, like it really is not.
Too many minus signs.
Too many.
No, you said the answer is yes and it's no?
So the answer is no. These do not come from Chern-Simons theory.
Thank you.
Okay. Jen.
The modular isotope G are they smaller than 49?
What new examples?
Well, you claim you have new modular isotope.
No. These are Mignard and Schallenberg's examples.
Oh, they are?
Yeah.
Oh.
Yeah, no, so Zheng Han was asking, yeah.
It's a reinterpretation of...
A reinterpretation, yeah, just a new construction of them. So for background, these modular isotopes that Mignard and Schallenberg talked about that I'm referencing here, these are digraph-Witten flavored things. These are just the Drinfeld centers of vec G omega for some special G in omegas.
But could you construct new ones with this?
That's what we're super interested in doing. Yeah, immediate question is, do all modular isotopes come from this construction? Yes. Can we use this to find smaller ones? And that's something we're actively pursuing. So yeah, maybe try to find some new ones. But at the end, I might sort of argue that maybe even if they exist, maybe we shouldn't care, even though I do. But okay.
Can I ask a question?
Sure.
Just a clarifying question. So if I take SU2 level 2 and consider zesting, what kind of modular tensor category will I get? Because as you said, they preserve the rank. So
that's rank 4. SU2 level 2, rank 3.
Yeah, it's going to be right.
Yeah, that's just this type.
Good.
Yeah. So I will mention I have some upcoming work where we basically do a systematic investigation of this question you just asked at low rank. So hopefully have a table to show you in a few weeks.
But could it be that it's not of the form G level K, but is uncondensation of something that is G level K?
Yeah, so it could be related to Chern-Simons theory in some less direct way. Okay. That's absolutely a possibility. But it at least, yeah, if you're restricting your attention to like realizing that exactly, it's not of that form. But yeah, if you allow yourself to throw in other constructions, that's a possibility for sure. Yeah. Well, that is a conjecture.
No, that's a statement.
So
Whatever you get, that can be proven. Whatever you can get from what is known as condensation
Yeah.
from Chern-Simons theory? Is it Chern-Simons theory for
Oh,
some
I
group?
thought you said everything comes from condensations of Chern-Simons theory. And I think that is a conjecture.
We're talking about the with invertible angle. Yeah. That's what you were talking about. For invertible, it's obvious. Maybe we're talking different languages.
Yeah, I may not have understood the exact question, but these are some examples. So on the one hand, this is a construction that relates theories that are very, very similar, and we may want to think of as the same. And on the other hand, it actually can do some things that are kind of interesting. Now, in order to tell you about why I've come around to thinking about this as a tool for putting different topological orders on the same complexity-theoretic hierarchy, I want to briefly show some pictures. So the first part of my talk, I was telling you about an absolute result, about the complexity of a specific theory, and there it was prudent to use F symbols. But when I'm trying to prove a theorem in generality, then sometimes it's more prudent to think about this the way mathematicians do. And so this is a totally orthogonal way of working with modular tensor categories, which is to work with them strictly. So this is as far away from being able to write down F symbols as possible. And in this setting, there's a graphical calculus. It's different from the one that you usually see with an F move with trivalent vertices. But the point is that all the nice structure that you have, associativity, braiding, twists, these all have nice pictures that go along with them. And it turns out that with zesting, you can understand what happens to the new theory just in terms of these local pictures and how they transform under this construction. And so all I want you to get out of this slide is that on the top row, there's some old pictures that I can draw in my original category, and on the bottom, there's some new pictures I can draw in my new category, and you see some boxes and some circles. The point is that this new stuff that you see, it just depends on the input to this construction, the zesting data. So old pictures, new pictures. But what can we do with that? This formalism is actually really nice because it lets you sort of see quite clearly that if you go and you look at what kinds of quantum circuits I can build braiding my anyons, they're going to have the same projective image in the unitary group whenever I sort of study a fixed collection of anyons. And it's actually sort of obvious from just the fusion rule considerations that the size of quantum memory is preserved. So these are the first two things that you ask about if you're comparing what two different anyon theories can do quantum computationally, what are the size of Hilbert spaces that I can build with them, and what kinds of gates can I do? And so this formalism lets you see really just in a proof by picture sort of way that, well, you start with maybe some anyon braiding on the left, it transforms on the right, and what you should think about on the right, the part of the picture that is sort of lying under our original braid, the zested part of the diagram, if you will, that's something that's only taking place on 1 billion anyons. So it's just going to contribute a phase. It's not going to do anything terribly interesting. All right. Lastly, I want to mention some more recent follow-up work to that observation, where using the same formalism, we were able to show with Sung Kim and Julia Plavnik that if you look at the link invariants that you get, so certain topological gauge invariants for your theory, that they factorize under this construction. So if I want to know what these invariants look like in my new theory, it turns out I can just compute them in terms of the invariants of my old theory, provided I compute this thing I've written here as J. So this is some other link invariant, which I want to claim as a classical thing. So the invariants split, they factorize under this construction, and in upcoming work with Calvin McPhail-Snyder, we show that there's a polynomial time algorithm for computing this sort of ratio between these invariants. And so, which isn't completely obvious from the get-go. So what this tells you, the reason I like this result, is that if you look at whatever complexity class, and you could say classical or quantum, that's carved out by the computation of these Reshetikhin-Turayev link invariants, it's the same under this construction. So here I've got my my complexity class diagram, and I've written something, highlighted in yellow, generically, maybe I have a modular tensor category, it carves out, the link invariants carve out some space in there. And if I replace B with B's zeta, it's going to occupy that same space. So not only sort of is the quantum computational power of these theories preserved under this construction, but so is these topological gauge invariants. Their complexity class is preserved. So just to wrap up here, I think a theme, like I said, for me has been, especially with the first result, that non-invertibility and topology are sort of connected through the lens of complexity theory. And with zesting, so going from non-invertibility to invertibility, if we're just changing something invertible about a theory, we don't expect it to change that much. And so zesting, I think, may be a useful way to sort of organize or classify topological order from a computational lens, because it really sort of relates theories that we really may want to think about as the same. There was, Parsip Anderson has a paper where he talks about some experiments that you can do to try to distinguish the 8 unitary modular categorifications of Ising fusion rules. And it turns out that you can't on trivial topology. So there's a sense in which, these kinds of observations, I think, support what you might see in experiment, but that's sort of speculative. And I'll stop there.
Questions?
Can I go back one slide?
Yeah.
So given that you have this factorization of the partition function, does it mean that the zesting basically is given by some tensor product of two TQFTs, or more complicated? Yeah,
really great question. So one thing I want to point out is that maybe I don't know if I would call this a partition function, because it's not the 3-manifold invariant. It's like a colored link invariant, but it's a kind of partition function we think about. Your question was?
Well, maybe tensor tensor product of
right. So for a while, I've been trying to make that idea work. Like, is there a sense in which I can think about this construction in a more elegant way, where I take my theory and I really just sort of stack it with something invertible, or there's some more intricate product that I take with an invertible theory. And another sort of point of contact with things that have come up in the program is that sometimes we see equations that hold on the level of a partition function, and they have, or we have equations that relate defect operators, and they have TQFT invariants. And so I think this is sort of a key to understanding, like, if there's a sense in which you can, understand this as a product with some invertible theory, maybe one dimension lower. That's what I think.
It sounds very interesting. Thanks.
Thanks.
I don't know how to use it. So what is the T in the formula?
That's a good question. So that was...
Okay.
Thank you. That was supposed to be a zeta.
Okay.
Thank you very much for pointing that out.
Let me ask
I didn't know when you asked. I was like, what is that? It was supposed to be zeta, so it depends on the zesting data. But it's the same colored link.
Okay. Let me ask the real question then. So for that invariant, it's determined by some abelian model of the abelian of your B?
Yes.
Okay.
Yeah. But not in a straightforward way. It's not as simple as it's not the Reshtikin-Turaev invariance for the abelian anyons. But it's, I think it we'll talk. Yeah, we can talk after.
Yeah, I have a question. So the link that's labeled, that statement's true for labeling by any simple object in the modular tensor category, or you have like a favorite one?
It's so L here, I can start with an arbitrary coloring by simple objects, And then J, I think about as the same link diagram, but it's colored by the graded components of those objects that I chose. So it's really a link diagram colored by elements of an abelian group.
Okay. And then in computing J,
Yeah.
could you just give some, is it?
So we had to do some weird things. We basically formulated this construction using 2 categories. And don't get excited, it wasn't fusion 2 categories. But we did some 2 categorical thing. And the main key ended up being that when we have our link diagram with components labeled by elements of the abelian group, we have to introduce region labels to keep track. So I think this is in some of Turayev's work, it's like shadow coloring. And it turns out that once you introduce these extra region labels, you can show that it sort of suffices to contribute this invariant just going crossing by crossing in your link diagram, which if you don't introduce those region labels, it's not obvious that you can do it in polynomial time in the number of crossings. Yeah.
It's probably not a very sharp question, but do you understand how when you have, say, a transient theory and you do some condensation, how that might affect complexity of,
Yeah, so I'm glad you asked that question, because I think an underlying motivation that my collaborators and I share, and this isn't unrelated to, I think, what Nat brought up, is understanding really rigorously what happens to the complexity of these invariants or the quantum gates that's under gauging and condensation of anyons. And this I sort of think about as like extremely modest progress in that direction, in the sense that I told you, you could think about zesting as sort of changing the symmetry fractionalization class of anyons. And there's a way to actually make that precise. And really, there's a generalization of zesting that I talked about today just for topological order to the setting of G-crossed braided fusion categories and to symmetry-enriched topological order, where zesting really is just exactly changing the symmetry fractionalization class of the defects. And so it's, very well understood. And when we think about gauging in the context of topological order, so not the high energy way, we first have to couple to background gauge fields, we have to extend, form this G-cross braided extension if we can, and then we equivariantize, then we sum over gauge fields. And so the zesting that I've talked about today kind of is this step that relates the torsor of different choices that you get at that intermediate stage of gauging, where there are different choices of how you couple to background gauge fields, but you want to be able to say that they're all kind of equivalent in some sense. Making that precise is a little bit tricky because these defects act on each other when they braid, and so it's understanding what kinds of logical operations you get and what kind of invariance you get is a little more delicate, but that's very much in the back of our minds, is that this is like a teeny little piece of that story, which is, at least by us, considered to be a hard problem. Like what happens under equivariantization, or just if you could track, going the other direction, if you could say what happens to these invariants under condensation, I mean, that's the dream, I think. Yeah.
I think I'm a bit confused by your last answer. So essentially you're saying that zesting is the intermediate process before you gauge. You're like coupling the theory to background field, but you're not promoting it to dynamical field. Is that right?
So when you couple to background gauge fields, there are choices of how you do that in this setting, if you can do that. And the claim is that in a more general sense that I've talked about here, there's a more general notion of zesting that says that those different choices are related by this construction. And so
I'm confused about how can this change some properties of the anyons? Because you are essentially just coupling your theory to some background field.
Yeah, great question. So I did not make this point super clear, but when you do this construction, you preserve the trivially graded component. So when I look at this construction for a symmetry defect theory, I'm leaving the anyons fixed, and I'm only changing things about the defect structure and how they fuse.
Okay. Oh, okay.
So when this, I didn't talk about this at all, but this more general version of the construction, you're leaving the anyons fixed, and you're just changing the symmetry fractionalization class of the defects. Yeah.
So it's very similar to G-crossed extension.
It is G-crossed extension.
Oh, I see.
Theory.
Okay.
Yeah.
Then this clarifies everything.
Yeah. It is the same way, and that was something we observed, but not right away. Okay. So yeah, it's exactly just okay. You can pick different G extensions of your trivial component, okay. And it's all the ways you can do that. Yeah.
Thanks. We have time for some other quick question.
Oh, I was just curious if there's any known thing about some complexity difference between solvable and non-solvable.
Yeah, I knew you would ask that. So I think Eric Samperton is working on that question. I think maybe what makes this slightly confusing is that like those notions are very like clear for a group, but when you talk about, like for example, a nilpotent fusion category, there are actually different definitions, and it's sort of not clear what the right one is. So to us. Yeah, I don't have anything to say, but my collaborator, yeah, you should ask him. Because whatever it is, it should line up with what you've been saying, your hierarchies. So we hope.
Is there a corresponding boundary module for the less?
Is there a bulk boundary? So you're asking like if I have like a gapped boundary of this theory and I zest not just the bulk but also like that whole picture, what happens? Yeah, I don't have anything to say right now, but that's something we're working on. Yeah.
Final question? Okay, if not, let's thank Colleen again.